Today, what we're going to do, we're going to move from area to volume. Our big deal on this, we're just now adding another dimension. So determine the volume of bright rectangular prisms with fractional edge lengths using unit cubes and unit fractional dimensions. So we're going to introduce this concept of unit cubes as well. Determine the number of cubes with unit fractional dimensions that have the same volume as a unit cube. And determine the number of unit cubes with unit fractional dimensions that can pack a rectangular prism with fractional edge lengths. So several different pieces we're working on. We're also going to connect two different volume formulas, where volume is length, width, and height, and volume equals the area of the base times the height. Liam? That's what the big B stands for is actually. So you'll see that. But we'll be working through that one a little bit. Homework tonight, 2 more Matthew spaces. That means that you guys are going to be up to number 18. You should have 18 finished. Okay? Open up your modules to page 87. As you guys will be able to see, we have a lot of vocabulary today. Guys, quiet down. We have a lot of different key terms because we're introducing a new concept, so we have to get all the terms that go with it. But before we get that, quick review on LCM. So this should take you guys, should take you about 10 seconds, but I will give you 2 minutes to find the LCMs for all 4 sets of numbers. How many of you were able to finish all 4 of them? Ooh, I was hoping for a little better hands than that. Okay. Guys, if you're using the cake, this is super easy. Who remembers our 4 key numbers? I have some that are still asking about it. Sophia?
It is 2, 3, 7, 5.
Whoa, don't know why I did that. Let's try that again. Here we go. 2, 3, 5, 7. Guys, get those down. You have to know those 4 numbers. That's your first 4 prime numbers. All the rest of the numbers build off of those 4. So, once I have that, 2 and 10, can I divide those both by 2? Yes. Then I do. Anytime I get to a 1 on the top line, I know I can't go any lower than that. So that means I'm done. LCM means all of them. So I'm multiplying all of them. 2 times 1 is 2 times 5 is 10. My LCM is 10. 3, 8. That one caused a lot of consternation. Can I divide them both by 2? By 3? So if I can't do one of my 4 key numbers, what number can I do? 1. Who remembers the math term for that when the greatest common factor is 1? You're actually kind of on the right track.
Really?
Relatively prime. Well done, Brandon. Relatively prime. You're actually, like I said, you were right in the bank. So if they're relatively prime, I just multiply the numbers. So it's 3 times 8, which is 24. Guys, 6 and 14, I can do 2. Gives me a 3 and 7. I'm done there. 6 times 7 is a 42. And our last one, 10 and 15, takes use of a new key number, 5. Gives us a 2 and a 3, which are my key numbers, so I'm done. 10 times 3 gives me 30. Literally should take you about that long, guys. These are not difficult. Is it making sense? Anybody still struggling with the cake? Good honesty, Liam. Guys, make sure you are practicing this if you're not comfortable with it yet. If you get comfortable with this, it makes all this very easy. That's fine. Upside down works the exact same way, Maverick. Guys, quiet, please. Okay, you know about 3-dimensional figures, such as cubes and other rectangular prisms. You also know how to operate with positive rational numbers. So given those, we're going to look today and open up the whole concept of volume. We're going to start with a thought experiment. I have 2 empty containers, each with a different volume, as shown. You also have a source of water. In other words, I can fill these 2 buckets up. Here's your task. Using just these 2 containers, a 3-gallon and a 5-gallon bucket, how can I measure out exactly 4 gallons? Okay? So I'll let you talk about it as a table. I'll give you guys about 3 minutes to talk about this. I will give you a couple of hints. Number one, there is no way to tell exactly how much 1 gallon is inside either buckets individually. Number two, my source of water is unlimited. There's a reason they gave you that. Does anybody think that they figured this out? Maverick.
Gallons. And then you want to add that to itself, which would be 4 gallons, which would be 924.
Okay, so you gave me the measurements, but how can I measure just using these containers exactly 4 gallons? So you did it mathematically, but I only have these 2 containers. How can I get exactly 4 gallons? Liam? Okay, but again, I can only use these 2 containers. How can I add them together? They gave that to us.
Which then you divide it by 2 to find the average in between it, which is 4 gallons.
So again, you just did what Maverick did. You've given me the number, but I need to physically measure 4 gallons of water. Sophia?
So I'm guessing when you're subtracting the 5 gallons from the 3 gallons, so when you get the 3 gallons, or when you get the 2 gallons, you're going to put it back to the 5 gallons, I'm guessing?
How?
By picking up the bucket and turning it over into the 5 gallons.
Okay, so it gives me 3 gallons.
And then,
So how do I get to 4?
and then you would fill up the 3 gallons just like a little bit, and then dump it in.
But again, there's no measures in that 3 gallon to tell me exactly where a gallon is.
Can I fall it?
No, it has to be exact.
You can get a good one.
Austin?
So it might be a slow process, but you count how much each drop of water is that comes out of the faucet, and then fill it out of the 3. Then you use that and keep filling it up to 5 gallons until it reaches 4.
Of all the solutions given so far, that's the closest to an accurate answer. You guys want to see the easy way to do this?
Yes, please.
I'll give you a hint. The key was I have an unlimited water source. So if I fill the 3 gallon bucket, how many gallons do I have? 3, which I can pour into the 5 gallon bucket, yes?
But
Then I can fill the 3 gallon bucket again, right?
Yep.
And how much of that will fit into the 5 gallon bucket? 2 gallons, leaving how much in my 3 gallon bucket? 1 gallon. So if I fill it up, totally exact, don't spill it. I know I've done 5 gallons. I have 1 gallon left in here, right? I can then empty the 5 gallon bucket, put the 1 gallon in, refill the 3 gallon again and put it in. How many gallons will I have in there? Does that make sense?
We're thinking it mathematically. We're not actually visualizing the buckets.
That's why, but that's the whole purpose of this exercise, is to get you guys to visualize what volume means. Because we want you to understand this is more than just numbers. Volume actually means something. And I can use that volume, in this case, to figure out exactly 4 gallons, even though I don't have a specific measurement of 4. So you guys all went straight to the math, which is great. I'm glad you guys were able to think outside the box like that. But we want you to understand that concept of volume is what's held inside of it. So is everybody starting to get that? So pull out your highlighters. We got our first highlight over here. So volume is the amount of space occupied by an object. Remember, guys, keep it down. An area. We always had to give our units in squared because I was doing a unit times a unit, correct? So for area, it was always unit squared. In volume, I'm doing a unit times a unit times a unit again, meaning it's always going to be in cubic units. Okay? So pull out your highlighters, highlight that one. Yes?
When you said think out, I'm glad that you guys think outside the box. Shouldn't you have said think outside the bucket?
That probably would have been a little better. I'll probably do that for A4 now. That's why we tape an A3, so it gets better through the day. Okay, everybody got this one? We're going to go ahead and go to the next page. Everyone turn to page 89. Keep your highlighters out. We have a lot to highlight on this page. Guys, please keep it down. Maverick. Supposed to have a highlighter right now because we're highlighting definitions in our modules. Okay, a polygon is a closed figure formed by 3 or more line segments. That's what we've been working with for our areas. That's the stuff like triangles, rectangles, parallelograms. Now we're going into 3 dimensions though. So a geometric solid is a bounded 3-dimensional geometric figure. In other words, it's something like this cube that I'm holding. I have 3 dimensions to it. Bounded means that there are sides to it. Okay? A polyhedron is a 3-dimensional solid figure made up of polygons. In other words, those are the ones that we've been talking about: squares, rectangles, triangles, parallelograms. A face is one of the polygons that makes up a polyhedron. A polyhedron can be made up of multiple shapes. A face is one of those shapes, the base shapes, that you will see. An edge is the intersection of 2 faces of a 3-dimensional figure. The point where multiple edges meet is known as a vertex in a 3-dimensional figure. So they've given us a couple examples using a rectangular prism and a cube. So our first one, figure A, is a right rectangular prism. The right rectangular prism is a polyhedron with 3 pairs of congruent and parallel rectangular faces. So all of the faces are rectangles. So it looks something like this, except that it's a square pyramid. So the opposing rectangles, the ones on opposite sides, are identical. Make sense? Right rectangular prism means it comes to right angles. Okay? So it means it's a rectangle, not a parallelogram. Figure B is a cube, which is a special kind of right rectangular prism. Cube is a polyhedron that has congruent squares as faces. So the big difference between a right rectangular prism and a cube is in a cube, all of the faces are exactly the same. In a right rectangular prism, the opposing rectangles are the same, but they aren't necessarily all the same. Does that make sense so far? Okay, let's add a little bit to our picture here to give us our examples on the vertex and the face. So they gave us the face, but they didn't really label the edge. So edges are these pieces right here where the back side and this side go. Here's an edge where the top and the other face go. Does that make sense? Okay. We also have vertexes. The vertexes are where 3 or more points meet together. So those are the vertexes. Can everybody see the different definitions and what we're actually talking about? So on the cube I'm holding, my edges are these sides over here. Vertexes are the points at the edges, where those edges come together. Okay? Good. So far, so good. Now, I'm going to just add this in right now. One bad thing on our recording for today. I've got wooden cubes and figures that I'm holding in class that you're not going to be able to see on the video, but hopefully you'll still be able to get the idea. Now, we've got a tank, fish tank. How can I determine the volume of this tank? I've given you a couple of hints. Multiply what? The height and Sergio? Length, height, and width. So the volume, to determine the volume, I need to multiply the length times the width times the height, just as we were doing in area formulas. One of the keys is actually identifying all three of those pieces on my figure. If you'll do that, it makes it super easy because all I have to do then is substitute those values into the formula. So, which of those three numbers would be the length? Ezekiel? Is it the length, the 30, the 50, or the 25? 30? Huh? Sure? Okay. Do you want to change it? What do you want it to be? The 50? Are you sure? Now you're sure? Last chance to change it. Okay. What is the width, Jaden? 25? You don't want to change yours? Okay. So Leanne, that means the height is 30. Do you agree with that? Okay, secondary question. Does it really matter what I call the length, width, or the height?
No.
Why not?
Because the names don't indicate the answer.
Oh, I think Tina nailed it. Say it again. Awesome, and he said the whole thing the first time. Community property multiplication. What am I doing to these three numbers? Multiplying. Does it matter if I do 30 times 50 times 25 or 50 times 30 times 25? No. So does it really matter what I call length, width, and height? No. Does it matter that I have all three of them identified? Yes, because I need to know what those three numbers are. Now, for the record, I actually do agree with how you guys did this. Length is normally what we would consider the side to side. Width is how deep it is. Height is the distance between those bases, the bottom and the top. Okay? But does it really matter? No. The key is make sure you have all three numbers identified. So once I've done that, now I can answer this. How many cubic inches of water can the tank hold? There's my question. So how am I going to find that? I'm going to just multiply it. 30 times 50, and we do those first because that makes it easy. 1,500 times 25 gives me 30 times 50. What's 3 times 5?
1,000.
What's 3 times 5? With 2 zeros. 1,500. 5 times 5 is 25. 5 times 1 is 5 plus 2 is 7. 2 zeros. 1 zero because I moved over, and then 2 zeros for the 2 zeros. 2 times 5 is 10. 2 times 1 is 3. So 37500. This is a word problem, so the tank can hold 37,500. Please do not forget your units, cubic inches. Any questions on anything we've covered so far? Is it making sense?
Yeah.
Okay, now we'll test you. I'll let you guys do number 2 by yourselves. I'll give you guys 2 minutes. Go. Then you do that. Okay, a platter box in the shape of a rectangular prism has a length of 3 feet, a width of 1 foot, and a height of 1.5 feet. How much potting soil can it hold? So I'm just going to use the volume formula. Length times width times height. Do you guys notice that every time I've done a formula, I write the base formula out without any numbers? Every single time I've done that, haven't I?
Yeah.
How many times have you seen me make mistakes when I have my base formula? There may be 1 or 2, but it's extremely rare. Why? Because if I have my base formula, I can keep track of all of the numbers that I need. Would you guys like to get perfect scores on your tests? I'm kind of showing you how if you'll do the work. Okay, now I know my length, width, and height. My length is 3 feet. My width is 1 foot. And my height is 1.5 feet. So as soon as I see a mixed number, I know immediately I'm going to need to slam dunk. I've got to make it an improper fraction. Is everybody okay with that?
Yeah.
So now I'm going to rewrite it just using the numbers. So 3 times 1 times 2 times 1 is 2 plus 1 is 3. Don't change your denominator. Now I don't have any reductions I can do, so 3 times 1 times 3 gives me 9. 1 times 1 times 2 gives me 2. 2 goes into 9 4 times with 1 left over. But what kind of problem is this?
Word problem.
Word problem. So my answer needs to be a
Word problem.
full sentence. Some of you guys still aren't doing that even on your tests. And I know we have talked about it every time we've done a word problem, have we not? Okay. So the planter holds. Don't do that with the chairs, please, Johanna. 4.5. Do not forget your units. Cubic feet of soil. If you did not put your units down, you are wrong. Yes, ma'am.
The way you did it when you were doing the 3 over 1 was so confusing. I was like, wait, where is he getting 1 over 1 from? Because all I did was do 3 times 1 is 3.
Mihana.
Multiply that by 3 over 2. And I'm
Destiny.
it was 3 times 1.
Callie's the only one that raised her hand to talk. Guys, have a seat. Hurry up. Okay, let's go to page 90. Did we skip a page? No, we're good. Page 90. Okay, on this one, now we're going to talk about unit cubes. All a unit cube is it's the same length and width and height in an even unit. So 1 inch, 1 foot, 1 yard. But it is all of 1 unit, okay? If I were to pack this right rectangular prism that is 7 inches wide, long by 3 inches wide by 5 inches high, how many cubes would end up being on the bottom layer? If I put them in by 1 unit, in other words, each cube is 1 inch long, 1 inch high, and 1 inch wide. How many cubes would I need to go across the front? What do you think, Austin? What do you think, Austin? Apologize, it's not band class. Your trombone practice there is not going to help you with this. I'm talking cubes that are 1 inch wide, and they have to cover 7 inches of space. How many cubes do I need? It's not a hard question. Okay? I'm using the same 1 inch cube, and I'm going to pack them going backwards for 3 inches. So how many cubes do I need? Does everybody understand so far?
Yes.
So how many cubes do I end up with on the bottom layer? 21. How'd you get that, Jet? 7 by 3. Does everybody understand that?
Yes.
Does it make sense?
Yes.
Now, the third part to that is, how tall is this? It's 5 inches. So how many layers of those cubes am I going to need? Does that make sense?
Yes.
So at my base, I had 21 cubes in it, correct? But I'm going to need 5 layers of that.
21 times 5.
Which would be? Does that make sense? So to fill this entire right rectangular prism, how many cubes do I need? 105 unit cubes, right? So There are 7 times 3 or 21 in each layer, and there are 5 layers. So I can pack the prism with a total of 21 by 5, or 105 cubic inches, or 105 unit cubes. Everybody good so far?
Yes.
You understand where all those numbers came from?
Yes.
Anybody not seeing it? Okay, so now we're going to take our next step on this. So we have the formulas for volume and prism and area of a rectangle. So this is the volume formula we've been talking about so far. The area, length times width, we all know that already, right? Because we just spent like 2 weeks doing that.
Yes.
Is everybody okay with that one?
Yes.
Here's our linkage. We just said the area of this rectangular face took us 21 cubes, correct?
Yes.
And then we multiplied it by the height of 5, right?
Yes.
Does everybody see that the length times the width is used in both of those formulas?
Yes.
Okay? So we're going to add a new term for you. And this is why it was so important that you be accurate when we're doing our area. They used a small b, because we are now going to do a large B. Okay? So if I use B to represent the area of the base of a rectangular prism, I can rewrite the area formula for B equals LW. So now my formula is V equals B times H. So I'm going to add a couple definitions for you, add them over here. So we have our small b, and that is the base of a polygon. That's stuff like the triangles, rectangles. We have the large B, which is the area of the base of a polyhedron. So add those two definitions into your modules. I'm sorry? Because it's the base of the polyhedron, so we call it capital B because it's the area of that base. Because then we're doing 2 variables, which gets more confusing. You're much better if you're only using 1 letter or indicator of what it stands for. Lauren? You can't wait 8 minutes? You can't wait 8 minutes, you mean? So how does this formula, volume equals the base times the height, relate to the example we just did? It's just like taking the total cubes on the bottom. So it's taking the total number of cubes on the bottom and multiplying by how many layers there are. We're copying down what's put on the board.
What's that?
There are
No, not that. What's that after cubes?
on the bottom.
Jeez.
So again, it's taking the total number of cubes on the bottom and multiplying by how many layers there are. In other words, what is the height? So using both of these formulas, you can rewrite the formula for the volume of a rectangular prism, V equals B times H, where V represents the volume, B represents the area of the base, and H represents the height. Okay, so our last one, hopefully we'll be able to get through before lunch here. So let's consider a cube that has side lengths that are each 1/2 inch. In other words, I take this 1 inch cube, and instead of a 1 inch, I'm going to use 1/2 inch cubes. Is everybody tracking so far?
Yes.
How many half-inch cubes does it take to fill the prism from the worked example? The one we just did, where we said it's going to be 105 unit cubes. So that's our worked example. Everybody tracking still?
Yes.
So this is the one these three students are going to talk about. Philip says it will take twice as many cubes to fill the prism. Mara says it will take 4 times as many cubes to fill the prism. Daniel says it will take 8 times as many cubes. Who's correct? Or is it all 3 of them? So I'll give you guys 2 minutes. Talk about it as a table. Tell me who's right. Is it Daniel, Mara, or Philip? How many of you think Philip is right? Raise your hands. Ooh, Tita, good job. Well, yeah, but Tita's saying Philip. Hands down, how many think that Daniel or Mara is correct? That it's going to be 4 times. Maverick, is your hand up? Liam, your hand's up. So you think Mara's right? Okay. How many of you think that Philip is right? Or Daniel, sorry. We already did Philip. Lauren, I didn't see your hand up. You think Mara? Okay, hands down. So it seems like most of you are on the Daniel train. So you think it's 8 times. Okay? So let's think about this for a second. I actually have an example for you that you guys can actually see. So I'm using these unit cubes. Guys, this is a half of a unit cube. So if I did 2 of these together, this equals 1 unit cube. Does everybody agree with that?
Yes.
So basically all I'm doing is I'm saying I've got these 2. Now I need to make this unit cube. So it takes 2 to go through the front, correct? Everybody good? It's also going to take 2 to get the depth, correct? It's also going to take 2 of them to get the height, correct? Is everybody good so far? Takes 2 in each direction. So if I set this down and I go ahead and build what we've just talked about, 2 by 2 by 2 to get the full thing, does everybody agree that's what the whole unit cube would look like then?
Yeah.
So, Lihanna, you want to count? How many did it take?
No.
You can count. I put it within your parameters. I know you can get this high.
Oh, I know. I know.
Lihanna, go ahead.
know. You said you're always right.
Count the blocks.
Just count them. I set them right there.
8.
8.
Yeah.
Good job, Lihanna.
I know.
You could do it. Well done. So how many did it take? So who was correct? Daniel was correct. Guys, quiet down. 5, 4. So we know that Daniel was correct. The key is it took 2 blocks in each of those dimensions to get all 8. Okay? And then I had to fill in on the back side to make sure that it made the full cube. So if you guys can now visualize what I'm holding, it makes sense? Okay. We'll finish. So given what we learned right before lunch, that Daniel was correct, how many times did he say it was going to take to fill the prism? 8 times. So let's go back to our example. So if we look at the initial cube, this rectangular prism that we have here, we said that one, it took 105 cubes to fill that, correct? If we replaced the 1-inch unit cubes with half-inch unit cubes, now how many cubes would it take to fill it? How many? How'd you get 440? 840. So I need to multiply that by 8, which makes sense if I really think about it. every one of these cubes over here is now being replaced by 8 cubes, right? So every one of those, 105, is now 8 cubes. So I just multiply the 105 by 8 to figure out how many I'd take. Does that make sense to everybody? Because now we're really going to stretch your minds a little bit. Turn the page. Go to page 91. So if you'll mark your text with me, you'll see we have a lot that has to be done on this. So we need to determine how many of each fractional cube it takes to fill a unit cube. Draw the fractional cubes on the empty unit cube. Then determine the volume of each fractional unit. So I've got 3 things. Determine how many of each. I need to draw them in. And I need to determine the volume for each of them. So first period really struggled on this, so I'm going to go through the first one with you guys to give you an idea of what it is that you are doing. So first part, and I'm going to be honest, determining how many is actually going to be easier if I draw them in first. So I'm going to start, I'm using a 1/2 unit cube, correct? Meaning, if it's a 1 unit, how many of the 1/2s is it going to take to cover that? 2 of them. So basically draw that in half. To go across the length, how many am I going to need? 2. To go up the height, how many am I going to need? 2. So what does it look like? If I draw it in, it's going to look something like that. Now I could just count how many cubes do I now have that fill this 1 unit cube. 1, 2, 3, 4, 5, 6, 7, and then the one I can't see in the back would be 8. So I need 8 1/2 unit cubes. So that answers the first part. I've already done the drawing, I've done the second part, but I haven't done the volume yet. So the volume is 1/2 by 1/2 by 1/2, correct? It's cubed, they're all the same. So 1 times 1 times 1 is 1, 2 times 2 is 4, 4 times 2 is 8. So they didn't tell me what the unit is, so I'll just use the basic of cubic units. Have I done all 3 parts that I was required to do? Yep. So now you guys need to do the same with the 1/4 and the 1/3 unit cube. And then, as a table, I want you to talk about how did you determine it and any patterns that stick out to you. So I'm going to give you guys about 10 minutes to do the next 2 and discuss those questions. Okay, on this one, we have now 4th unit cubes, meaning if I'm going to draw my picture, I need 4 across. 1, 2, 3, 4. I'm going to need 4 across the front. So that gives me 1 layer. Is everybody okay on that?
Yes.
So how many total cubes would be on that layer? It's 4 by 4, so that's going to be how many cubes in there? 16. So that first layer has 16 unit cubes. But I also need to do going up. So I've got to go up and do 4 layers of this. So I extend all of those through 4 layers and across the top as well. I now have 16 on each layer, meaning I had a total of 64 1/4 unit cubes. Does everybody see that?
Yes.
So my volume is 1/4 times 1/4 times 1/4. So 1 times 1 times 1 is 1. 4 times 4 is 16. 16 times 4 is 64. And again, they didn't give us units, so we'll just use the basic of cubic units. So each one little cube has a volume of 1/64 cubic units. If I did the third cubes, now I'm just going 3 across on each of those two directions, and then 3 high. So it's going to look something like this. So on this one, I've got 3 by 3. So how many cubes are on that bottom layer? 9, because it's 3 by 3. The second layer is going to have 9. The third layer has 9, meaning I have 27 1/3 unit cubes. My volume, 1/3 times 1/3 times 1/3. 1 times 1 times 1. 3 times 3 times 3 is 27. And that is cubic units. Do not forget that all my units today will be to the third power because I'm doing 3 different dimensions, length, width, and height. Making sense so far? How many of you got all those right on your own? 2 out of 3? Okay, so several hands are up. That's not too bad. So how did you determine the number of fractional cubes that filled each unit cube? How many of you did like I did and drew the picture to figure out how many there were? So for me, I drew the picture. And then counted. Okay? Part 7, describe any patterns you notice between the size of the fractional cube and the number of those cubes that filled the unit cube. Did you guys notice any patterns? Sophia?
The more you went on, the smaller it got. Like the answer. Since the fourth is the biggest bottom number, the answer is the smallest at all.
Okay. So the more cubes I use, the smaller the size of each one was. Did you even notice anything about the denominators and the total units needed? Brandon? Good. The denominator showed me how many I was cutting in each direction. Did you guys notice? When I had half unit cubes, it took 8 of them. The volume was 1/8. When I used the 1/4 inch cubes, it took 64 of them. The volume of each was 1/64. When I did the 1/3, it took 27 of them. The volume was, see the pattern? My denominator gave me how many cubes it would take, which, if you think about it, makes sense. If it's 1/8 of a unit, then I'm going to need 8 of them to fill it up, because that would be 8/8. If I need 1/64, then I need 64 of them to fill it up, because 64 over 64 is 1. The other one is, because these are all cubes, meaning the sides are all the same, all I'm doing is taking the cube of the denominator. So 2 to the third power is 8. 2 times 2 times 2. 4 to the third power is 64. 4 times 4 times 4. 3 to the third power is 3 times 3 times 3, 27. Make sense? Any questions on anything we have covered today? So we've gone through the unit cubes. We've gone through finding the volume. We understand now that if I have the volume equals the big B times the H, the big B is actually saying the area of the base. Okay? So this should lead you into your Mathia for tonight. Again, 2 workspaces. You should be at 18 total at this point.